Natasha, your turn.
Okay, thank you, Alhari. We start with session 4.3, and question number 1 is: the Paris Agreement committed states around the world to work to limit global warming within 2 degrees. What do you see as the role of the sector in achieving this? And we have 4 long answers: to respond to demand and maintain compliance, to reduce internal carbon emissions, to focus on minerals and metals that facilitate the green economic transition, or to work with manufacturers and governments on long-term high-impact options. After answering, please scroll down to the question number 2. And it will be: the people of Europe expect better and better quality air, water, and use of land reflected in progressive environmental legislation. How do you feel this has impacted the mining sector in Europe? And the answers are: compliance requirements don't lead to a difference in liability between projects in Europe. It has led to positive changes in mining in Europe, ensuring better assessment and mitigations. It's a limiting factor to business and desincentivizes exploration and mining in Europe. And also, although it adds challenges to mining in Europe, the continual improvement of regulation in Europe drives improvement worldwide. And then please scroll down the page to the question number 3. And it is: with increasing pressure to ensure that people and the environment are protected not only during operations, but during closure and beyond, what measures would provide the most benefit? Closure planning requirements are already too onerous and should not be augmented. Best practice is closure provisioning, and planning should be statutory for both planned and unplanned closure, post-closure, and land restoration plans, but non-financial provisions should always form part of an updated mine plan, or it should be a statutory requirement that mine sites should be restored as far as practicable to the original pre-mining land use. Okay, thank you.
Thank you, Natasha. Okay, so we're here at the Building the Green Mining Industry session. So this session will continue until 12:45, not 10:30 as actually mentioned in some of the programs. I will allow Richard not more than 10 minutes, so please keep control of the time, and I really actually appreciate that you have a very big job of controlling 7 speakers. Just again, announcement about it tonight. So if you're going to join us for the gala dinner, the buses will be leaving at 18:30. So if you're late, we're not going to be waiting for you. We'll be leaving at 18:30. So please congregate in the lobby at 18:20 if you're joining us for the gala dinner, because the buses cannot wait because of the traffic and so on and so forth. So 18:30. If you're late, then take the taxi and join us at the restaurant, What You Need's restaurant, and the address is actually on the program. So without further ado, Richard Oldcorn is the Managing Director of SRK Consulting, will be moderating this session. Thank you, Richard.
Good. Thanks, Arthur. Looking? Good. It's always encouraging to see that the answers to the questions were the right answers in the way that we framed them. So we're all on the right page. Glad there were lots of zeros for the wrong answers there. We've got 7 great speakers here today who are kind of developing the themes we've had over the last day and this morning, legislation, stakeholder engagement. What we're talking about now is how we can put some of these things into practice to actually try and, provide technical solutions to, creating that green mining economy, limiting the environmental impact, recycling waste. So they're fascinating talks. There are 7 of them, which is why I'm perched on this little stool at the back. We'll try and keep to their times. We'll try and get some questions in at the end. I'm sure there'll be questions. So let's kick off. Oh, now you can hear me. I won't repeat everything I just said. We'll start with Stephen Pearce, who is the Technical Director at Mine Environment Management, and he's going to kick off this session with his talk on technology to optimize waste management approaches and improving project economics, reducing risk, and demonstrating sustainability. So take it away, Stephen.
Okay. Firstly, I'd like to thank Bleeden, who are the main sort of sponsors for a lot of the research you're about to see. And I'd also like to thank the organisers for having a session on green mining and for everyone to actually come and listen to talk on green mining. I know that green mining or environment is often viewed as secondary to things like financing, production. That's mainly because a lot of green aspects, I think, are viewed as a cost, not so much as an opportunity. But in reality, our brains, human brains, are wired for opportunity. That's why you have investment, stock market bubbles, gold rushes, everything like that. Everyone looks for the opportunity. So I think what we should try and do is to reframe, look for the opportunities here, and then that way we can perhaps try and view green mining more as an opportunity than a cost. So what do we mean by optimization for waste management? Essentially what we're saying is we try and achieve a reduction in waste volumes, maximization of ore volumes, reduction in the life of mine risk profile, so with respect to liabilities such as acid mine drainage, demonstrating sustainability over the full life of mine, and reductions in the cost of waste management. So all these things are optimization of waste. And the key sort of themes that we're playing on here for my talk is going to be smart mining, so this is using technology, sustainable mining, so a holistic approach to demonstrate life of mine planning approaches, and efficient mining. So by efficient mining, I mean we take an approach that reflects the true life of mine costs. So if we look at what I would say is current best practice waste management, pretty much now everyone is moving towards having at least block models of waste. So we are classifying waste materials, we understand what there is. And increasingly we're moving towards using a mining approach to waste. So we're mining the waste out of mining. All the principles of mining are being more applied to waste zones. So there's a little video to illustrate this. Essentially, grade control drilling is done in ore zones, but now is more increasingly done in waste zones. And the reason for that is you can validate block models, and you can get a much better idea during the mining process of what you're actually mining. From that, we can optimize waste dig plans, optimize the extraction of waste, essentially, and also feed into actual mining programs. So most mines track where things are going. So in this case, what we're doing is actually tracking right from the beginning, the block model, through to the mining, through to the placement, all the volumes and where the waste is going. This is really key if you want to optimize waste management. You have to mine the waste the same way you mine the ore. But the key assumption here is that what's in the block model is actually reflected in what's mined. And I'll talk about fragmentation because this is a key aspect to this. So we look at what is ore and what is waste. Commonly, cut-off grade is used to define the difference between ore and waste. So there might be some hard cut-off. This above 1,000 ppm is always ore. There's some marginal area which may or may not be ore, depending on prevailing conditions. And there's material that will always be waste because the grade is too low. This marginal area is often viewed as low-grade ore, but I would also say it could be viewed as high-grade waste. Okay? And this is important because if it's viewed as waste, generally speaking, it's given zero value. But if it's high-grade waste, it has a highly negative value because the cost of managing highly sulfidic material is significant. You can easily go over $10 million by the time you've looked at water treatment or cover systems. So even if it's net cost neutral to mine material as ore, over life of mine, it's actually probably better to do that than call it waste, unless you're fully accounting for the costs of treating it as waste. And why that's important is when we look at fragmentation, what's ore and what's waste can change. So it's well known that the particle size controls geochemical properties. So after blasting, sulfides, metals, carbonates, they often go into the fine fraction, which means that the waste material that you're mining can have a different property to what's in the model. The same would apply to ore zones, which is where there's a whole series of investment at the moment into increasing efficiency of ore recovery. The fine fraction of the waste accounts for more than 90% of the risk. So most of the acid mine drainage risk comes from the fine fraction, not from the coarse material. And this is only probably 20% of the volume. Standard waste classification systems, they don't account for particle size. So what happens in most waste management programs is you mixing small volumes of high-risk material with large volumes of low-risk material. And that's a missed opportunity for waste management and also a missed opportunity for recovery of metals, which I'll explain. This is important because this is now coming on to the opportunity cost. So from the point of view of fragmentation analysis and technology, there's quite a lot of off-the-shelf technology. So this is Orica's FragTrack system. You can link this with portable technology like XRF. So the technology is available to be able to look at the effect of fragmentation. This is mostly applied to ore, but as I'll explain, we should also look at applying this to waste zones. So during a blast, if we just have a look, this is a bench from a gold mine. The actual block model says that this material is low grade, sulfide content less than 0.3%, which, as a rule of thumb, mining industry and consultants tend to adopt. This is low risk material, less than 0.3%, there's no environmental problem. But after a blast, this is just showing the blast face. If we zoom in on a piece of material that's been blasted, you'll notice there's a big cavity. Now in that cavity were sulfides. The shock of blasting removes these sulfides out of the cavities. This is because the sulfides are generally weaker structurally than the host rock. So what that means is that after blasting, all those sulfides go into the fines. So although this is 0.3% low risk, actually what happens is that virtually all those sulfides report to the fine fraction, which is the high risk fraction. So if we look at compositional variation with a blast, the fragmentation profile is important because it dictates both the particle size of the product and the degree to which concentration of metals can occur within the fine fraction. Coarser particle sizes have a smaller surface area, finer particle sizes have a bigger surface area. The reason why that's important is that the surface area influences the degree of the speed of the reaction of sulfides with oxygen, which is where you get acid mine drainage from. So, like I said, the finer fractions, they're smaller, they have a higher surface area, they are much more reactive. If we're also getting concentration of sulfides into those fine fractions, it doubles the problem up. So this is some data from the site, and you can clearly see, going through the grain size fractions, sulfide content is increasing in the fines. So you've got higher surface area, higher sulfide grade. Calcium, which is a neutralizing agent, is actually staying the same. So we're not seeing the same process between the calcium and the sulfur. So in acid mine drainage waste characteristics, a lot of the time it's buffering and acidity projection is used to characterize it, but in the material that ratio can change depending on the fraction. So again, this fine fraction, which may be perceived to be low risk, could be much higher risk. Then, if we want to look at the opportunity aspect of this data is showing particle size on the x-axis, and on the y-axis is grade of nickel and copper. And it's a distribution plot because it's on a lot of samples. And you can clearly see that if we put a cut-off grade arbitrarily in here at 1,000 ppm, the coarser material is waste. So our block model said it's waste, and it is waste. However, the fine material is actually above the cut-off grade, it's actually ore. So this is waste material, contains some ore-grade material. Why that's important is that you're actually concentrating in the things you want to recover in these fine materials, and they're also the same materials that have the high risk of acid mine drainage. The fine material also is basically ore-grade material, higher AMD risk. So this variable distribution of metals and sulfides indicates that your bulk properties of your waste don't necessarily reflect what's in your drill core samples or in your block model. So we're basically missing a potential opportunity here for recovering ore from waste and minimising AMD risk. So if you look at the components of this is the block from the block model. After it's blasted, we get a large volume, 60% or something, of coarse material, less than 10% of the surface area, has a lower metal grade than the average block, has a lower sulfide grade than the average block. It's generally got a low environmental liability. The fine fraction, which is less than 40% of the volume, has got more than 90% of the surface area, it's got higher metal grade, has got a higher sulfide grade. So there's a high environmental liability cost here, but also high potential for metal recovery. If we look at how most waste rock dumps are managed, we take all of this material and we throw it in a big heap. So you're mixing these high-grade ore fines with low-grade, low-risk waste fine, coarse material. And the problem with that is that acid mine drainage comes from reaction of oxygen and sulfides. If you mix in coarse and fines, you're encouraging oxygen there to get in. So you actually mixing the two materials together is the worst thing that you can do. Even encapsulating this material doesn't necessarily work, because although it's called encapsulation, you're still mixing coarse and fine, you're still getting air into there. Typically, the solution then is to say we'll put a cover system over the top of a waste dump at the end. Now, whilst the technology is somewhat proven, this is mitigation, it's not prevention. So this is still quite a high-risk solution to assume that at the end you can solve the problem that you've created by not optimizing your waste placement. And again, treatment is another possible solution, but you're still treating a problem that could have probably solved in the beginning. So the opportunities here to optimize waste management are first in identifying the waste in the ore. So this is making sure that we're looking at doing grade control drilling in the waste zones, not just the ore zones. We're looking at fragmentation analysis and making sure that what we're calling waste is waste and what we're calling ore is ore. Recovering ore from waste, it's very feasible to recover fines. Screening technology is well established. Installing a screening plant doesn't incur high cost. Dry screening is actually a fairly low cost solution. And the other thing is, if you're screening off the fines, you can bypass primary and secondary crusher and send this stuff straight to the mill. So although there is a cost of recovery, the cost of processing drops because you're not going through the crushers, and oftentimes the primary crusher is actually a bottleneck in expansion of mines. So you can potentially expand your ore production without even having to install more crushing capacity. You can reduce the volumes of high-risk material. So like I said, these fines, they're the high-risk material. If you can get rid of them, you're actually reducing 90% of your problem by dealing with 10 to 20% of the material. This is a much more efficient way of managing this high-risk material. And you can reduce the requirement for large-scale engineering. So you don't need complicated big cover systems if you've prevented the problem in the first place. And there's also potential to manufacture rehabilitation materials. So by pulling off fine materials from low-risk zones, you can actually use these in things like cover systems. If you are going to use them, you need finer materials. So using fragmentation analysis is actually useful for that too. So from an overall process, we're looking at mining waste as ore, incorporating fragmentation analysis into the process, actually using the technology we have, which is grade control block models, to model waste and ore zones better, and potentially inserting screening processes to start to try and recover these fines and separate them off, leaving the coarse material for waste dump, which is lower risk. And one more thing before I finish, and this is that at the exploration stage, there's also technology now to use where you can kind of predict this effect. So XRM is technology that's now available, and you can actually look in 3 dimensions inside a drill core, look at the distribution of sulfides, the association of base metal sulfides with iron sulfides, association with carbonates, is it in veins, is it in fractures, so this technology is available, and you can actually predict to some extent what's going to happen after mining and blasting to your materials to say, is this waste potentially going to be ore, or can we recover the high risk material easily? Thank you.
Thank you. That was very interesting and nice visuals as well. It was good to see. Next up we have Robert Goddard, who's a senior resource geologist at SRK in our team in Cardiff in the UK. Rob's going to talk about looking at recovering mineral resources in historic mines, in old remnant parts of historic mines. Very topical, considering some of the presentations we've had over the last couple of days in Central Eastern Europe, lots of these types of things. For those of you who remember back to the early 90s, Galmoy was an old mine started in the 90s, but it's very relevant to what we're talking about here in this region. So go ahead, Rob.
Okay, yeah, thank you, Richard. So my talk is on how we can develop mineral resources from remaining mineralization in historic mines and effectively brownfield exploration, and it's particularly relevant for this sort of greener mining aspect, obviously, because if we can work on getting out the mineralization that's remaining in current mines, then obviously it'll help to reduce our overall footprint from other mines. And my talk is focusing on particularly how we can be smarter in the choices that we make in terms of which brownfield sites are taken forward for resource development, and that's going to be illustrated by the way of a couple of case studies, and the main one of which is historic lead zinc mine in Ireland. So firstly, just to take a step back, in terms of brownfield exploration, why is it attractive compared to greenfield exploration, for example? So I just got a couple of examples here. So on the left-hand side, we have a picture of a typical greenfield site undertaking some virgin drilling, and obviously the advantages of a greenfield site are that the sky's the limit in terms of potential. Then you may discover another world-class deposit, but obviously the downside being that potentially it's going to cost you multiple millions of dollars and many years to get to an advanced exploration project and accompanying resource. And of course, only a small percentage of exploration projects become mines, as we know. So in terms of brownfield sites, this is an example of an old open pit in West Africa, and the advantages obviously being that there's great exposures, and so you can straight away work out what's going on with the geology. So here are some sort of mapped on contacts, and we could see where the mineralization was hosted and get a feel for its continuity and thickness. So all sort of key aspects that you need for developing a mineral resource. I guess one of the slight disadvantages is that depending on the amount of data you've got, there may be uncertainty as to whether was the better mineralization already mined out, and is the remaining mineralization, is it now thinner, less continuous, and perhaps lower grade and poorer suited to processing. So that's certainly a consideration, sort of particularly when you're working with not much data. So in terms of how we go about assessing the attractiveness of brownfield projects in general, of course it sort of depends on technical and economic attractiveness of that project. But the thing I'm going to focus on in my talk today is one key aspect, which is data support. And this is important in considering if we can develop mineral resources from historic projects, because data support underpins sort of the main key aspects that need to be considered and demonstrated when reporting mineral resources in compliance with international codes. So that covers everything from the coverage of the data, the quality of the data, the understanding of the controls on mineralization, getting the confidence in the grade continuity, and also ultimately whether there's reasonable prospects for mining what remains at that mine. And importantly, even once we've got a mineral resource, if things are positive, that data support aspect is critical in being able to develop more confidence in that mineral resource ahead of more advanced mining studies. So for my first case study, I'm going to just briefly talk about a North African lead silver mine before moving on to the second case study, which is a bit more in depth. And basically the background here is our company, SRK, were commissioned to take a look at what data was available for the project and get a sense of what amount of work would be required to develop a resource from it. So in summary, we visited site, we issued with a few historic documents initially, and based on initial observations, there were certainly attractive aspects of this project. So this is a picture in one of the open pits, and we can see here below that yellow line is the host rock to the mineralization, hosting lead-silver mineralization, which is relatively close to surface. You can see there beneath a sort of a mudstone overburden. In terms of wider prospectivity over the wider area, there were outcrops of this same host rock over several kilometres in area, suggesting potential scale of a potential reopening of the mine. And based on a couple of historic documents, there seemed to be structural controls that controlled paleo channels which hosted much higher grade zinc. So again, another attractive feature to potential future mining. However, on sort of further investigation into what was available, it turned out that on closure of the mine, and in the 1970s, after its sort of about 10-year operating period, all the data was either discarded or lost, and so effectively, in our opinion, the mine was back at a fairly early exploration stage, with a requirement to effectively re-drill and resample the entire project to get something that would be considered at a reasonable stage for a mineral resource. So the outcome of that case study was that the investor decided to not take the project any further. So, and for my second case study is the Galmoy zinc-lead project in Ireland. And so before I go into the project details, we were commissioned again in a similar role to assess what data remains and what's the potential of redeveloping a mineral resource there. And so this map on the left just shows a picture of where the project's located. And if we were to jump into a more local scale geological map on the right-hand side, I think the key sort of observations and takeaways that we found were that the mine was located within a dolomite host, stratigraphically hosted, with structural controls, and the main takeaway from these observations that it was situated on quite a prospective trend known as the Rathdowney trend, where several historic operating mines had been located, so really highlighting the potential attractiveness of reopening a mine there if it looked attractive based on our review. So just to give you an idea of just some basic geological characteristics, here we have sort of a project scale picture of the mine. On the right hand side is a picture of the drill core. So just to briefly summarize, they were massive sulfide bodies hosted in zinc and lead in sphalerite and galena mineralization. The thickness of the ore bodies ranging from 2 to 25 meters, on average 5 meters thick. So essentially, and it was this drill core that allowed the development of the mine initially, which led to the image you can see on the left-hand side, which are a picture of the plan view of the mine workings at the mine, with the different colours showing different status of pillar resources, remaining pillars at the mine. And so that was particularly useful in having the layouts of those maps, which really mapped out nicely and confirmed the extents of the well-known mineralisation. And the mine itself operated between 1995 and 2012, and during that time, production was in the order of 8 million tonnes at a grade of about 13% zinc and 3% lead, so reasonably attractive, certainly by today's terms. Importantly, when the mine closed, the company that were operating it gave all their data to the Geological Survey of Ireland, so created a really detailed and organised repository of all the mining and exploration data. So our first step in seeing what was remaining to support resources was to go through that data, and there were 4 key data types in our opinion that really helped to potentially support resources there. The first one of which being drill hole data. So the project had some 2,000 drill holes, both underground and from surface, and you can see a cross-section here through a conceptual mineralization model. And this really helped to give some comfort in terms of understanding the exploration scale, geological and grade continuity. In terms of mapping data, there was a significant database of underground mapping, and here we have an example of one of those map faces, and the way that they did mining at the project is for in the key areas they produced face maps in the development drives every sort of 5 to 10 meters. So this image, small image on the left here, is basically a picture of what they see in the face. So really gives us good confidence in terms of where the mineralization waste contacts are, and particularly when compared to just a narrow cylinder of drill core, that's a great step in the right direction in giving us confidence in what's actually going on. And in addition, there were composite face samples taken from that face, so again, in areas where we don't have drilling, we could get a good indication of what the average grades are doing in that area. So a great help in terms of understanding the mining scale continuity. The third type of data that was useful was a very detailed underground mining survey that was based on total station data, and which you can see illustrated in black, and the coloured bodies there showing the modelled mineralisation. And so this really helped to understand what mineralisation was remaining and what had already been mined. The final set of data that was really useful in helping us to understand what was the quality of the data or what was likely to remain was production records. So being a publicly listed company, for every year they operated, they reported out the tonnage and grade they were getting. And so whilst there is some uncertainty to what parts of the mine this material came from on a year-by-year basis, we certainly had some good confidence in the average grades of what we see in the database, in the drill hole database. So with this in mind, I guess the conclusion was, there's a lot of historic data there that could be useful, but there was obviously still uncertainty as to whether it was reliable for input to mineral resource estimation. So we suggested to the company that they go away and do, in the first instance, a targeted verification drilling program to try and support that historic database. And the results of one of the areas drilled is illustrated here. So this long section we see on top is an area from the southern part of the mine, and we're looking at a bit of a sort of a 3D long section where the thick cylinders represent historic drill holes, whereas the drill hole here with the dashed trace showing the verification hole into that area of the mine. And in terms of takeaways observing from how this new hole supported the old, there were three main takeaways we could conclude, and these include support for geological grade continuity, and you can see here that the new hole quite nicely supports the sort of the lower grade, more sort of is actually iron-rich mineralization at the top, hence we get a drop in zinc, and then in the middle we get the higher grade zinc confirmed over the sort of the widths and geometries expected from adjacent historic holes. In terms of data quality, that new verification drilling was submitted to laboratories with a full suite of quality control data that gave us good confidence that the new data was within an acceptable tolerance, and given that we've got adjacent intercepts of that new hole next to old, we could get the takeaway that the range of grades in the historic were supported by this new verification data. The third main takeaway was a couple of these verification holes actually intersected old mine workings, and they intersected the old mine workings in the position we expected, so either sort of hitting a void or hitting backfill material, so ultimately giving us confidence that that historic depletion extent was accurate and we could rely on for resources. So our conclusion from the verification drilling that was done was effectively we had sufficient confidence in the historic database that we could take it forward into redeveloping a mineral resource for the project. And so what we're showing here is a block model and the drill hole grades that we were able to develop in the southern part of the mine. And ultimately, the company were able to use that as a basis for more advanced exploration studies and more advanced mining studies for their next phase of investment and trying to get the mine back towards operations. So that concludes my two case studies, and obviously the second case study was a positive outcome from being able to use historic data. And just as a conclusion slide, really, just to sum up, obviously the brownfield exploration sites range from projects that have very little data through to data that have significant high amounts of data. And for those projects with very little data support, the main takeaway is that there's obviously significant work may be required to develop a mineral resource associated with high time and cost investment associated with essentially re-drilling the project. Whereas on the flip side, if you have a project with significant historic data support, potentially there's potential to save cost and time in redeveloping resources, providing verification drilling supports that. And so really, focusing on projects with significant historic databases, I think can be considered as a way of conducting smarter brownfield exploration with the potential to save costs and time in developing these projects towards mineral resources. And so that brings me to the end of my slide, so thanks everyone for listening.
Thanks, Rob. It's very interesting. Next, we have Maria Nacheva-Schwarz, who's the manager of EnviroChemy's team here in Bulgaria and also based in Switzerland. Maria a PhD in Bulgaria. She's Bulgarian, worked in Germany, and is now back managing the team here. So she's going to talk to us about mine wastewater treatment and some examples of good practice. So go ahead.
Hello, everybody. Thank you very much for the introduction. I'm here to speak about wastewater, and in particular about the wastewater coming out from the mining industry, based on some good practices. Okay. Thank you very much. I'm representing the company EnviroChemie, and what is EnviroChemie doing? EnviroChemie is dealing with any kind of water around the industry. In your particular case, in the mining industry, our competence are into, of course, wastewater treatment or water recycling internally in your production, or recovery of some precious metals or some valuable substances. We are based in Frankfurt and doing this since almost 44 years. What we are doing actually for the wastewater, we're choosing the technology, supplying all the equipment, bringing it on site, assembly it, putting into operation, and of course doing the performance of the plant. Afterwards, we're ready to support our customers for additional services. So we are something like 19 companies worldwide. One of these companies is in Bulgaria. Enough advertising. Now speaking about this certain project or several projects I would like to present you. And this is one of the biggest coal company based in Russia. For us engineers, it was important that our customer has 15 mines, so it was a possibility to have a long-term relationship and develop also our technologies, because we adapt every time our plans according to the customer needs. Of course, for my financial directors, other figures were important, but all of these figures were okay. So here, to go into the project, this is a table of average wastewater of a coal mine. This is not only SUEC, it is all of our inquiries we got for coal mines worldwide. I tried to make an average example, what is a typical wastewater from this production. Usually, these waters are not very polluted, actually. But in Russia, everything is a little bit different. So, as you see, you have lots of suspended solids, and it varies, of course. And usually in Europe, if you go to the 50 milligram per liter at the outlet, it is perfectly okay. But in Russia, you have to go to 5 or 10 milligram per liter, it depends on the site. And of course, in Russia, if you have in your wastewater zinc and it is around 0.005, you have to go to the metal precipitation step to go lower than 0.001. So these wastewater in generally are not so polluted, but we have to go through the whole chemistry to be sure that all the parameters are accordance to the law. In the other case, the mine can lose his license, and this is of course a huge risk. So these are several projects we done for SUEC. I'm just showing them to give you an overview what was the water amount we were treating for this customer, and it varied something between 100 and 1,200 cubic meter per hour. So if you have 100 cubes an hour or 2,000 cubes an hour, it's a huge water amount, and you have to do a chemical precipitation for your heavy metals, and you have to also to flock and fell your suspended solids. This means the whole chemical plant result, because it depends what kind of chemicals you are adding. You have a certain time for a chemical reactions, and if this time is 40 minutes, so in one water volume of 2,000 cubes an hour, it's a huge reactors. And SUEC was definitely not thrilled to make such huge concrete reactors, and also to make very, very big secondary clarifiers in order to separate all the flux, all the sediment, heavy metals put already into insoluble compounds and take away from the system. So we were forced to think flexible, and if it's possible with a very small footprint, because the space was a problem. Don't ask me why. So each project starts, of course, with the testing, sampling, doing some laboratory homework. I'm not going to the whole procedure, but here's some pictures from the laboratory. It came out that the chemistry is working very well. We're building very big, very stable flux, and the clear water was completely clear from all the traced elements and compounds. And these flux usually are going down. We are sedimenting them. That's why secondary clarifier. But in that case, it appears that with a little help for example, of one flotation unit, we can float them up. And if we float them up, then we have a very small footprint for the future wastewater treatment plant. So, as I mentioned, both methods are okay. Smaller footprint flotation unit. A little bit lower in investment would be the concrete solution. So SUEC decided if we have a small project below 300 cubic meter an hour, we will take a flotation unit. If we have a bigger project, then open. This will be open, sedimentation or flotation. How is a flotation unit working? I have only 15 minutes, and in this room there are lots of professionals, so I'm really not going to explain you a unit you're dealing every day with. And for the lawyers, I guess this is only a black box, but it is maybe okay. So the important thing I would like to mention here, is we're using also chemicals as you did in your flotation unit, and in order to squeeze the space, we put also lamellas inside. So the first plant we built for SUEC, it was 2013, and we were a little bit conservative, the customer also. That's why we put our flotation units into building. It was 2 times 175 cubes each, including also sludge dewatering unit. This is how it looks inside. This is the flotation unit, and this is our chemical part where we're putting our chemistry. And this is here the result of the water treatment. So the second project was a small project, and it should be flexible. So we wanted to move it from one side to the other side. That's why, and it was not very critical, because it is only 3 times 30 cubic meter an hour. It is very easy to put it into a container unit. And it was a huge success, because they liked this solution very much. The next project, the water became bigger and bigger, and we were forced to put our flotation unit again into a container, but to achieve 90 cubes an hour for one module. That's why we developed our twin modules. And here you see the opening ceremony, happy SWIG people and board of management, and again water results optically. In the meanwhile, our first project became smaller for them. The capacity was not enough for the wastewater, so they wanted to extend, but please not into a building, do it again into container unit. We put our two twin modules, and in that matter, we achieved 50% increase of the capacity of the plant, only with 1/3 of the footprint. So they look in such a matter outside of the container before putting them inside, and this is the already ready solution for transport to Russia. And the last project was actually from the water amount pretty tough, because we had to deal with 1,200 cubes an hour. And that's why we developed our new containerized unit. My colleagues call the T-type container, because we have 8 containers shaped as a T, and I call them T-Rex because each of these units has 2 flotation installation inside, and each of these flotation installation has a 200 cubic meter an hour. So if you place such a T-Rex unit on your site, you will be able to treat 400 cubic meter an hour wastewater. So, and these are the results from, again, from a SWIG site. In average, we succeed to achieve suspended solids in about 1.3 milligram per liter. So, I guess I have enough additional time, but I would like to put it later for questions. Thank you very much.
Thanks, Maria. That's all very interesting stuff. Thank you. Next up is Martindale. It's a slight change to the proceedings. It was supposed to be Jamie Spears. Jamie hasn't been able to make it, so Richard is doing the presentation. Richard heads up our tailings team in the UK and Europe. He's a principal engineer, and so he'll be more than happy to talk about the future of tailings management, which is obviously a very topical subject for anybody trying to develop a mine or get something permitted in the future. So away you go, Rich.
Thanks, Richard. Thanks, everybody. Jamie sends his apologies. I hope I make an adequate substitute for him. If we'd been stood here perhaps 10 years ago and we'd been talking on similar topics, these are some of the future trends that we might have been discussing with regards to mine tailings. And largely, the focus was on dewatering occurring in the plant. Taking water out of mine tailings in order to try to reduce risks associated with the movement of mine tailings, uncontrolled movement of mine tailings, and also in conserving water resources, which are often scarce in environments where mining projects are being undertaken. The idea is, in terms of the what we're seeing on the chart here, is to remove excess water and, if possible, some of the entrapped water, so that we're dealing with less volumes and that we're dealing with safer materials. And indeed, over the last 10 years, these sorts of projects have indeed come on stream. We are seeing paste, thickened tailings, dry stacks, where filtration plants have been used to remove as much water as possible from the tailings. We are seeing these being developed, the technology is advancing, the state of the industry is moving forwards. Current areas of focus, the photographs here are obviously things that I'm sure people in the room are aware of. The problem that occurred in Brazil, the major tailings dam failure that occurred, the Brumadinho Dam that failed in January of this year, has obviously focused the mind. I attended a conference once where somebody quite rightly said that the link between the mining industry and the public is unfortunately often mine waste failures. This is when the public and mine interaction occurs very uncontrolled environment. In this case, it resulted in a lot of deaths, hundreds of people killed. We have to do better. And the areas of focus are largely in relation to that. We must do a better job. Consequences of failure are a topic under discussion. BHP have recently issued some results of some audits that they've undertaken and some assessments following the failure here. And they have put into public domain that they have 5 extreme consequence tailings facilities. These are facilities where there is potential for deaths to be counted in the hundreds and significant environmental damage to occur. And this was reported in things such as the Guardian newspaper. These are not industry papers, this is public. Consequences are obviously very important. Liquefaction, these are the methods whereby a seemingly solid material behaves like a liquid. There's a lot of focus on what's triggering this behavior. It is not just seismic loading. What are the other ways that liquefaction can be triggered, causing these massive failures that we see? Upstream raised tailings dams. This is a commonly used technique for building tailings facilities across the world. Following the problem in Brazil, Brazil is talking about banning upstream raised tailings dam facilities. Inspections and reporting. Many of you probably are aware, the press reports that facilities had been inspected and were indeed being looked at, and yet these issues still occur. Are the inspections and reporting being done properly and well? Legislation and regulation. There is discussion ongoing at the moment about whether we should be focusing on a global strategy for managing mine tailings, trying to bring practices in line and trying to make sure that there's some oversight in the whole industry. Pollution, environmental impact, of course, extremely important. Conservation of water resources, closure and long-term management, climate change, levies, taxes and insurance. There is a big focus on tailings. If we look, this paper that's referenced here from Casey, it's somewhat old now, but still the messages are important. If we look at the historic reasons why tailings dam failures occurred, truth, it was technical issues. It was issues that were occurring that were not well understood, that people didn't realize consequences of. But in more recent times, the causes are primarily management of failure of management, and also the weather, climate change, what's more rainfall, etc., that is occurring. So these are important trends when looking forwards into the future. We're moving away from failures being attributed to technical reasons towards failure of management and the weather, climate change. So all of this, and a lot of what we're talking about, has been to do with the green economy, the circular economy as well. How can we use these wastes better, what can we do in terms of designing waste out of the system? If we can get rid of this waste, we can get rid of, minimize, etc., all of these major problems that have occurred historically. And there's a lot of focus on this in the industry. We have a conference every year specifically on tailings and mine waste. There is a lot of focus on this. How can we reduce the amount of waste? How can we better use it in other forms? Some of our presenters here have been talking about these things. Obviously, the chart here, if we can improve the environmental legacy, we may also be able to improve the economic value. So these are some stages whereby we can perhaps upcycle waste and improve things, use it for good purposes. Most facilities that I visit would fall very much down at the bottom end there, bottom left. Contaminated waste, it's a negative environmental legacy, and it's negative in terms of economic value. How can we move things further up the chain? And we're working hard to try to improve things. This is interesting little example. At Mount Keith in Western Australia, as part of the tailings disposal, they are getting a cemented carbonate material forming in the tailings dam, which is sequestering carbon, CO2. And in fact, what they found was that quite by accident and by coincidence, 10% of the mine's annual greenhouse gas emissions could be offset with what the tailings were taking up. This was without any attempt by them to do this. And now they're looking to see if there are any ways that they can improve that and increase the uptake. There was a paper issued that said there is possibility of mine tailings to sequester somewhat in the order of 400 million tons of CO2 on an annual basis. This is potentially an opportunity for waste to become something useful to us. Now, a lot of problems with mine tailings are all really due to water. It's the water in the tailings that causes us problems. With the way mining projects are going, the grind sizes are getting finer, and it's more difficult for us to pull the water out of the tailings before we send it out to storage facilities. So there is areas of research looking at new ways of removing water from slurries. One of them is using electrokinetic techniques. There's nothing really that's been looked at on a commercial scale yet. This is more research purposes. But in the case discussed here, what we're doing, the water in mine tailings contains ions. If we can use an electric charge to get those ions moving, perhaps those ions can bring water out of the material with us. And what's very interesting with this research is that it's quite independent of the grain size. So these finer wastes, finer grain size slurries, there's potential opportunity for this technique to be used to help us dewater it. The finer the grain size, the more effort that we need to squeeze this water out. With particularly fine material, we often have to go to extremes such as press filters. Very, very costly to buy and extremely costly to run. So we're looking at some alternative ways whereby we can dewater these fine grain size wastes. Another important point is perhaps using already available tailings facility and tailings areas via better means. This is an example from Mexico here, where an old slurry tailings dam has been converted into a dry stack. The area of the tailings hasn't changed. The old tailings facility had relatively poor factors of safety. Can we improve its safety? Can we get more material in here? Other ways of doing this. This is an actual case. So the top chart there is the factor of safety current that was in the facility when it was a slurry facility. Factor of safety of 1.3. The new scheme, the pink coloured material is new, dry stacked waste placed on the old slurry. Factor of safety has indeed improved, but they've had to manage water in the old facility and pore pressure in the old facility. So this system has used an old tailings dam to good advantage and use for the company going forwards. They've had to dewater the old facility. They've had to pull the water out with pumps, but the water they found had a nice silver content in there, and the mineral that they were able to recover from the water that they were pulling out, which was necessary to get the factor of safety up, has paid for the pumping systems. In just 2 months of operation, it had covered the cost of the wells. I should say that we're looking at a similar solution for a mine site in the area local to us here at the moment. We're working on that right now. This is another way that we may see going forward for management of tailings and mine waste. Can we use waste rock to help us with some of the problems with slurry? Can we use small cells whereby waste rock demarks the boundaries, using the waste rock to help us pull that water out, to improve the drainage, to make the whole facility stronger? And again, there are places in the local area to us here where just this solution is being used. Ultimate goal, and I think that this is a way that we're going to see the industry moving forwards, is in co-disposal, using the waste rock and tailings together to improve the management of both. So the waste rock mixed in with the tailings will improve the strength of the tailings, and the tailings in turn will encapsulate the waste rock and potentially will help us with managing acid drainage. Very briefly and quickly, as I'm overrunning here, I apologize. We're also looking at using remote sensing to keep an eye on tailings facilities, particularly where is the water, how big are the ponds, where are seepages occurring. We are using technology to help us manage monitoring data coming from tailings facilities. Rather than a data gathering exercise, it must be a monitoring exercise. We don't just gather data, we have to know what that means. If we're seeing sharp rises in pore pressure and piezometers, these dashboards can help us manage that data and can help us with our clients to say there is a problem, it's developing, let's deal with it. Final slide is some good, effective tailings management practices. We've known how to build these things well for a long time. The fact that we're not doing it is not good enough, and we must do better. Thank you very much for your time.
Thanks, Richard. It's fascinating stuff, and again, developing all the time. So just now to have yet another part of the green mining economy, we're talking about mineral processing. John Viega is going to deliver a talk on measuring particle size in concentrates, mineral concentrates. And John is Vice President of Global Sales and Services at Sidra Minerals Processing in the US.
Yeah. Okay. The video will work.
He's got a video as well, so here we go. Very exciting.
Good afternoon, everyone, and it's a pleasure being here, and we thank Arthur and the committee for the invitation in the second year. And I must say that Arthur and his team, have done a splendid job, in my opinion, organizing this event. The communications have been superb. And the time limits are really appreciated. I mean, I never studied so hard on a presentation the night before to make sure I didn't go over because, you know, when that card comes by, you get a little bit nervous and you got to cut it short. So I really did have a dream that the minute came up, instead of the card, a button was pushed and the floor disappeared and I disappeared with it. In any event, thanks. I hope this is meaningful for you. Today, I'd like to focus on leveraging an innovative and unique technology in concentrators, this in copper, but it operates in gold, zinc, and all kinds of metals. And really using this particle size, real-time particle size measurement system to optimize net metal production in an automatic control loop. And hope to show that when you look at instrumentation, regardless of what it is, it's important to have real-time information, but as well, it's key to learn something from the data, because technology or information in and of itself, if you can't learn something new about your process and start to identify and eliminate variables, you really can't maximize your throughput or recovery. So my presentation outline is really in 4 pieces. I'm going to give you a quick overview of the scissor technology, and I'm not going into a lot of detail because we do have a booth here and we can dive deeper into how the technology works. We're going to look at conventional particle size analyzers, measurement devices, versus the real-time particle size measurement technology called Cyclone Track PST. And then look at some early adopters, just one slide. And then finally, we're going to look at a preview of a disruptive technology. And we heard a lot about technology adoption yesterday. We heard hearing a lot about the trend towards controlling tailings ponds and conserving water. So we'll get a little bit in that. I think, I don't know if this works. No? I mean, I could just talk to this slide. Okay. All right, folks. That's of course, a schematic of the ball mill circuit, and you can see the water and the ore, the feed, going into a sump and being pumped through. Now, in order to control a circuit, you need an accurate flow measurement and an accurate density measurement. Conventional flow meters, like the electrical magnetic meter, is a mass market flow meter, not really designed specifically to address the challenges of a mining slurry. A lot of times, if you do have air or bubbles in your slurry, what happens? Well, the meter measurement is measuring both the slurry or the fluid plus the volume of the bubbles. This passive sonar processing flow meter has 2 outputs, one volumetric flow and one gas void fraction, or the percent of bubbles to the fluid. Therefore, you could adjust the accuracy to the proper true liquid level. Number 2, density is really key, accurate density. Whereas the error in measurement of a volumetric flow meter is linear, so 2% in trained air is 2% error in your measurement. For the density meter, it's not so. It's dependent on the specific gravity or density of the slurry. So the lower your density gets, or specific gravity, you could have a 2% error in your offset measurement on the density, but that could be translated into a 10% offset in your solids mass flow rate. So that's quite significant. And you definitely need the both those measurements to control particle size, which we'll talk about now. Okay, so can I get back to the presentation, Andre? Now, just like in sports, they kind of cut the clock, right? No. Okay. So let's look at what's being used today in concentrators to determine the measurement of the particle sizes. Since 1970, they've been using these sampling systems. Again, they're designed for the mass market, not for specifically the mining industry. So they're highly unreliable, a lot of maintenance, they require recalibration periodically, but in my mind, the biggest thing is that they make a measurement, not in real time, but in batch mode. So in this example here, I'm sorry guys. Okay, in this example here, I'll hit the right button. Each one of these cyclone clusters draw off a sample from a consolidated overflow and takes about a minute and a half to process. So that by the time the operator gets all the particle size information, which as I said is consolidated, it's one consolidated number, it's 9 minutes. Whereas the cyclone track PST, as you can see here, again, as you can see here, is inserted into each one of the cyclone overflow pipes, specifically to get a particle size reading and a bead on what's happening in each one of these cyclones. So each cyclone could behave very differently than each other. It's not one ubiquitous measurement. It's real time and it provides measurement every 4 seconds. And the important thing is that it enables real time control of the process. So what are the converging forces and enablers that drive this technology? And again, I heard yesterday that mining companies are slow to adopt. Well, that's true to a certain extent, but you need a disruptive technology and you need to have barriers removed to have that adopted, but a lot of times the economics and the environment will drive the adoption. So in this case, what's helping drive adoption of real-time individual particle size measurements are the forecast of higher demand due to the growth of new technologies like the EVs we were talking about yesterday. Environmental constraints, we heard about the sustainability of water and life of the mine or ores, and also regulatory restrictions. And talking to a couple of mines, they had to limit their throughput because it's capped at a certain point, and that's a license to operate issue. The pressing need to control the ball mill and grinding circuit to maximize value is by balancing recovery, throughput, and cost efficient. But we all know that throughput and recovery, you get trade-offs. So there's a model that's developed called the net metal production model. And what that does, is it maximizes the throughput and recovery and head grade equation and maximizes the net metal production, the valuable metal production. So if I may, in this case here, we know that throughput and recovery are strongly correlated to particle size. And when you use the net metal production model, expressed by that equation, throughput, recovery, and head grade, you're maximizing the metal that's produced. If you look at a traditional recovery and throughput curve, vis-a-vis the net metal curve, if you were just trying to maximize recovery, you would be suboptimizing your net metal production. And likewise, if you were trying to maximize your throughput, you would be suboptimizing your net metal production. Here, also using this model and PST real-time measurements, you could, by controlling a set point in particle size, you could push right against that process barrier and not violate the downstream. And this third chart here, if you do have PST control, you can increase your recovery by 1.77%, but grinding coarser, you're increased 2.75%. So just quickly, two early adopters. I won't go through this. We heard Geo Techman and Eurasian yesterday, but I do want to say that there's common denominators in early adopters. One, there's a culture of innovation and continuous process improvement. Two, there's formal visionary programs and long-term programs to adopt new technologies and increase metal production. And both of these companies as well, we see a lot discontinued use of the sampling systems because they just don't serve their needs for automated control of the circuits. I think the big thing that Eurasian really stuck out in my mind, I mean, you heard all about the increase in recovery and everything, was that they learned things about their process that they've never learned before. And so I do want to just go through a couple more slides on this. Well, with the PST particle size measurement system, you could employ two strategies concurrently. One, macro strategy, so you tie it into your automated control system to maximize your net metal production and control your final product size. And there's a micro strategy whereby you could look and get data on each individual cyclones. They don't all act the same. So for example, in the picture to your left, you can see when there's a rise in pressure and flow, that cyclone number 9 goes out of class. And what happens is that there's a reduction in the circulating load. And the mass going through cyclone 9 dominates the consolidated flow going into the flotation cell. In the second one, there's an increase in sag feed, and essentially the same thing happens. You can see cyclone 7 going out of class, and then coming back in, and then going out of class again. So what you could do there, when you see that, you can either reset your cyclone or switch to another cyclone you have in reserve and that may not have that much utilization on it. Okay, 1 minute? Ah, good. I missed a trapdoor, I hope. All right, so PST, if you have real-time particle size control, what you could do is actually enable yourself to take on a trend that's happening in the industry today, and that's coarse particle size recovery. And flotation's been around for over 100 years, and no matter what they do, they're going to have the same issues. Where the elephant in the room is that there's such a narrow range of particle size that could increase or optimize recovery and throughput that it just never get there. So if you have and can grind coarser, what you do is flatten out that curve. So very selectively, you can either grind coarse and don't worry about downstream processes, or pick up and grind fine. So basically, this technology is very distinct from flotation. It has high selectivity, and it's in early stages of commercial launch. So That's about it. And to me, I think it fits nicely with the prior presentation because the coarser you can grind and the less water that you use, the better off you'll be downstream. And by the way, when you think of it, the technology can also be used in tailings. So thank you for your attention and appreciate it.
That's great. Thanks, John. Very, very interesting, and yeah, nicely dovetailed with Richard's talk just before. Of course, we planned it all like that in advance. Next up is Melanie Cox, senior geochemist from SRK in Cardiff office in the UK. She's going to talk to us about mine waste characterization, another very, very topical and constantly changing subject. So, you okay there, Mel?
Yep. Thank you very much. Thanks for the opportunity to present to you today. Yeah, as Richard said, I'll provide a bit of a high-level introduction into mine geochemical characterization of the mine waste, the implications for the project, and put some context in relation to EU legislation, which in my experience is sort of fairly poorly understood in a lot of areas at the moment. And so just to provide a bit of an overview, what I will cover, introduction into what the geochemical risks are, an explanation as to why the characterization is necessary, and then an overview of how this is actually done and how that feeds into the European legislation and what implications that has for your project. So I think most people already know, obviously one of the major risks is ARDML, acid rock drainage and metal leaching. And as we know, our sulfides such as pyrite are brought up to the surface area is increased, and they're exposed to air and water, subject to oxidation, and result in the release of metals and obviously acidity. The other thing to consider is the substances that may be introduced into your waste as part of the mining. So obviously you've got nitrogen-bearing compounds from blasting, and also things like cyanides from processing. So where are the risks associated with basically any aspects of your waste facilities? You've got waste rock dumps, tailings storage facilities, pit walls during mining, and pit lakes post-closure. Also in underground workings, the wall rocks, in your heap leach piles, in temporary stockpiles. And the Extractive Waste Directory specifies the amount of time that material can be left on surface before it is actually classified as a waste facility. And understandably, this depends on the geochemical behavior of your waste. So anything non-hazardous, non-inert, you're allowed up to 1 year. But obviously, people do stockpile with the intention of backfilling underground, but it's just to reiterate that that waste will probably still need to be classified as a waste facility in the short term. So just to sort of demonstrate the importance of geochemical characterizations, obviously, if you get your mineral resource estimation wrong, it's going to have large cost implications to your project. If you get inefficient mining methods, it's going to, again, have large cost implications to your project. If you get your mine waste management wrong, it has the potential to put a halt on your project. We heard about the delays associated with permitting through Garant yesterday, and it can really just halt everything, particularly if your permitting is affected. So why is the geochem characterization necessary? There's basically a twofold requirement. So firstly, you do need to comply with the legislation. And in Europe, the main overarching legislation is the Extractive Waste Directive, the 2006-21 EC, which again we heard about yesterday too. And you need to comply with the permitting requirements, so you need to understand this in order to have a permit to operate any waste facility. It requires a waste management plan to demonstrate that you're minimizing your waste, you're doing your treatment and recovery and disposal of any extractive waste. And the sort of second fold is that the geochem characterization can really drive your project design, so it can influence and inform decisions surrounding mine planning. It can reduce your long-term liabilities, so it is much better to design a facility up front than pay for long-term ongoing mitigation costs. And it can influence closure planning. And the graph that I've included there actually was, I think, one that was also touched on yesterday, highlights where Bulgaria was actually shown as the highest waste producer. And this was extracted from a document, Best Available Techniques document, and it was what member states reported during 2004 to 2014. And although it does obviously highlight the waste producers, it's worth noting that in 2017 a document was produced highlighting big gaps in countries' understanding or member states' implementation of the Extractive Waste Directive. So this graph really does just highlight where the companies are reporting it, but not necessarily the true picture. So just to provide a few case studies, quite well-known case studies for some of you, I'm sure, of why the characterization is necessary. You've got Iron Mountain Mine in the USA, a massive sulfide deposit. It stopped mining in 1963. They were underground and open pit mining, and it actually resulted in fracturing of the mountain and a huge amount of sulfide oxidation. The sulfides became exposed. It resulted in extremely acidic waters, and they put in a water treatment plant in 1994, which was estimated liabilities of around $1 billion at that site. In Wales, we have about 1,300 mines that are impacting on 67 Welsh water bodies. It rains a lot in Wales. These are all legacy sites. They're reliant on funding. The funding is often restricted just to the top 10 worst sites as well. And so because of the funding, remediation is predominantly passive treatment systems that vary on site but can cost anywhere around 600,000 to 1.2 million per site. And you've got the Wheel Jane mine down in Cornwall in the UK, a former cassiterite mine, where they were pumping water to their tailings facility. They had a technical issue and resulted in this huge plume of water that was actually released into their nice touristy bay, highly acidic and containing a lot of heavy metals. And back in 2014, they estimated that they were going to need to continue treating the water. They installed initially a passive treatment system and then an active water treatment system. They were going to need to continue treating the water for another 50 years, and the costs were around about 1.5 million per year to run that. So just to give a brief overview of why the characterization process, and then I'll go into a bit more detail on the next slides. So we do a representative sample selection, and this is key. It drives everything else, that all of your data relies on this, so it's key to get this right up front. We do a number of static and kinetic test works. We do need to allow sufficient timing. Timing is important, and it shouldn't be an afterthought in your mining. It needs to be upfront as part of the mine planning. You also need to allow sufficient time for running long-term tests, particularly if they're feeding into your permitting applications. So it will enable your predictions for acid rock drainage and metal leaching. It enables you to classify your waste facilities according to legislation. And it can be coupled with baseline studies in order to predict potential environmental impacts. The legislation is particularly confusing. It is also often being updated. It can be country specific. We use a number of these guidance documents. There is the Best Available Techniques document and GUARD guide, and a technical guidance WM3 on hazardous waste classification. So just to go in a little bit more detail, sample selection, as I said, it is very important, it's key. It must be representative of your future waste. It must be, I suppose, spatially and lithologically representative. And you need to consider things like the low-grade ore. It's obviously project-specific. It depends a lot on the complexity of your project and the stage of your project too. It's worth noting some of the difficulties. It can be difficult to get representative samples. Obviously, early on, a lot of the drilling is focused on the ore body. And tailings in particular can evolve as the processing evolves and as the processing is refined. So you just need to bear in mind that you need to refine your characterization program too. The test work costs that we do, similar short-term static tests, longer-term kinetic tests. Obviously the short-term tests have lower costs. These can include things like a multi-element assay, which will enable you to determine if anything is actually elevated in your waste. And then the higher rate tests, the kinetic tests, the longer term tests, will quantify the actual rate of any acid generation or metal leaching. The tests that run in terms of the kinetics, they actually can be lab-based, such as humidity cell test work, which simulates like a waste rock dump. We do monolithic leach testing to simulate any cemented paste backfill materials. And you can also run field scale cribs, which is similar to humidity cell, but under field conditions. So I touched on timing. It must be done upfront in the design and planning. It can ultimately drive your design, your mine design, but it should also be reviewed as part of the operation and closure. And you need to allow enough time for the long-term tests. Costs, obviously there are costs associated, but the costs that you're putting in up front can often save you a lot of money in the long term. It is much cheaper to manage your risks up front than to treat a leachate in perpetuity. Financiers also have a high interest. We heard a little bit this morning on the risks associated with the project, and a lot of financiers understand that geochem risks are a big impact to projects, so financiers often have a high interest in the level of geochem studies that have been conducted. So it will enable you to assess the balance of acid-generating sulfides and acid-neutralizing carbonates. It enables you to understand your metal release, potential metal release. It does also recognize what is your good material, so it's not just about identifying the bad. So it enables you to identify materials that can potentially be used for road building, safety berms, dam building, and hence prevent waste altogether and complying with the waste hierarchy. So in terms of the legislation, the European classification process, waste needs to be given a European waste code, and this is not a mining-specific legislation. It applies to all waste. So the extract there is just for waste rock dumps. There are separate ones for tailings, but a lot of waste rock falls into a code which is 010101, waste from mineral metalliferous excavation. And this in the guidance is actually classed as an automatic non-hazardous entry, and the guidance does say it's automatically non-hazardous without further assessment. However, you must be aware that the extractive waste directory still requires you to assess those potential impacts. So there's a bit of a disconnect there in the legislation, and you cannot just call it 010101 and do nothing else. Materials are classified as inert or non-inert, and this is predominantly based on sulfide content and heavy metal content. There are a few other criteria that trigger that too. Waste is characterized as hazardous or non-hazardous, and again this is another non-mining specific bit of legislation, and it does focus a lot on the chemical composition of the solid material. It gives minimal consideration to mineralogy and leachates that may be generated. So again, you need to have a very holistic approach. Consider the Extractive Waste Directive alongside these other legislations, and it's really important that you're assessing your leachates and assessing any impacts to ground or surface water. The hazardous classifications will then sort of trigger a Category A, so Category A facility for any waste that is characterised as hazardous, and obviously there's other implications that would trigger a Category A, such as your failure or geotechs. The other thing just to point out there as well is excavation voids are not actually classed as a waste facility. However, there is still the need in the legislation to check that your waste when going back underground, if you are going to cement paste backfill, is not going to have an environmental impact. So again, you can't just ignore the fact that it's not a waste facility and get away with it. So in addition to complying with the European legislation. And just to sort of recap on a lot of things, it can be coupled with numerical predictive tools to assess environmental impacts. It drives project design, it informs engineering decisions such as capping and lining, it identifies materials for reuse, it enables selective handling or sorting, reduces costs and post-closure liabilities. It also demonstrates to demonstrates to local communities your interest, your high level of interest in the protection to the environment. And then just finally, the Extractive Waste Directive does require a waste management plan, so all of the characterization of your waste, the classification of your facility does feed into the mine waste management plan, amongst other things. You need to also describe the impacts to human health and the environment, so all of these studies will help you do that. And the waste management measures then lead into the environmental risk and impact evaluation using the source, pathway and receptor approach. Thanks very much for listening.
Maybe if we're lucky we'll get some questions at the end, but we're sort of running out of time a bit. So last but by no means least, we've got Anna Mladenovic from the Slovenian National Institute of Building and Civil Engineering, and she's the head of laboratory there. So welcome, Anna.
Thank you, Mr. Chairman. I would like to thank to the organizing committee for giving me the opportunity to speak here at this important and interesting event. I would like to present 3 projects which are running in the frame of EIT raw materials program and which are all highly relevant to the topic of this conference. But first of all, allow me a few sentences about our institute. It is Slovenian National Building and Civil Engineering Institute, established 70 years ago, located in Ljubljana. Legally, we are public research institute in the field of building and civil engineering. We are government-owned, however, we don't get much money from the government, so we are on the market, application-oriented, addressing the real day or the real life needs of the industry. So we are open for cooperation and searching for possible synergies between our institute and entities from industry and from other branches. And now a few facts about EIT, because I believe this entity is not very well known to you, to audience. It is European Institute of Innovation and Technology, established in 2008 as an independent body of European Union with the aim to increase the capacity for innovation. And this is the first initiative that brought together all three sizes of knowledge triangle. That means business, academia, and research centers. And EIT, as a mother, then has established several innovation communities, and one of these communities is EIT Raw Materials, dealing with the whole raw material value chain. That means from exploration, mining, processing, recycling, substitution, and to the eco-design. There are 6 collocation centers across Europe and the headquarters in Berlin. Since 2014, EIT Raw Materials granted many projects on the subjects that I have just mentioned, and our institute is currently running 3 such projects in the RIS program. What is RIS? RIS means Regional Innovation Scheme, and this is the program or the tool that has been established by EIT Raw Materials in order to increase the innovativeness or innovative index in some countries of in the European Union. So many of those RIS eligible countries are in the EC region. EC region means East, South, East part of the Europe. That means Western Balkans and this area. And also Bulgaria is RIS eligible country. The fil rouge or the main theme of all projects that I'm going to present now is I will start with the screening. Identify the historical tailings in the region, go there, take the samples, analyze the samples, find out how to extract the metals. As you know, historical depots or tailings contain a lot of metals. Then find out how to recycle the residuals after metal extraction. Find out how to reclaim the area in terms of environmental and geotechnical issues. And on the top of that, create a network that will be a network of relevant stakeholders in the area, and hope that this network will be able, after the project finishes, to become a seed for future activities in this field. So a short presentation of all projects. One of them is RIS-CURE project, Zero Waste Recovery of Copper Tailings in the EC region. This is an ongoing project with a lot of partners from different countries. Most of them are from Balkan region. Apart from that, from Finland, Spain, and Slovakia. In the end of the project, the partner was also Bor Mine from Serbia, but in November last year, the Bor Mine was sold to the Chinese, and they are not interested in anymore, so this is quite a disappointing situation. The aim of the project is establishing a self-sustaining network of copper value chain stakeholders in the region, evaluation of the technologies which are appropriate for extraction of metals, and for this purpose, 2 tailings will be addressed to check which or what kind of technologies or set of technologies are the best. And this will be, we hope, a small step to the increased competitiveness in the region. The second project is RIS Recover project, Regional Innovation Scheme for Zero Waste Extraction of Critical Raw Materials. In this project, we focus to North Macedonia, addressing the historical tailings and the metallurgical heaps in order to find out the quantity, quality of the metals, which technology would be the best, and of course to create a platform of stakeholders which will be able to survive also in the future, not just in the period of the project duration. And of course, also in this project, the important activity is how to recycle the materials after metal extraction, how to beneficially use these materials in civil and building sector, and also maybe in other sectors. And the third one is this Restore project, evaluation of red mud tailings in the EC region, and of the extraction of heavy minerals containing rare earth elements and other valuable metals. This picture is Ica, Hungary, a few years ago, spill of red mud, large environmental disaster. This project is still in the preparation phase, starting next year. Consortium is quite large, since the project itself is quite complex. We have one partner from Great Britain. We don't know what will be the fate of these partners. Maybe if Brexit occurs, then we will lose this one. And there will be a bunch of task partners from this Balkan region. Task partners are partners from RIS-eligible countries. They are not officially partners of the IAT raw materials, but they can participate, they can get some money without paying any fees. Aim of the project, extraction of first scaling, mapping the region, extraction of heavy minerals out of red mud, use the residuals in building sector, and of course establishing a network of relevant stakeholders. Some technical data. It is estimated that in this region there is approximately or more than 85 million tons of red mud. So we will address 5 tailings in 4 countries. We expect that available technologies which are used for extraction of heavy metals from other types or from ores, different types of ores, will be also appropriate for extraction of heavy metals from red mud. So this was my message to you. If you are interested in cooperation, you can cooperate in those projects that I have presented just now as a stakeholders, or you can be a partners in the future projects. So in this case, please contact me. Thank you for your time.